For the last talk of this session, we have Felix Linker from ETH Zurich. He's going to be talking to us about the formal analysis of Apple's iMessage PQ3 protocol. So very different from the two previous talks. I hope you enjoy.
Yeah, thank you. I also wanted to start with saying it's very different to the previous two talks, but I guess I don't do that now. So in 2024, Apple released its new iMessage PQ3 protocol, which they claim to be the new state-of-the-art in quantum secure messaging at scale. And iMessage PQ3, as its name suggests, is an end-to-end encrypted messaging protocol that is used in iMessage, but also other Apple services. iMessage PQ3 comes with 5 security goals that I've outlined here. So first and foremost, it's an end-to-end encryption protocol. So its main goal is secrecy. So all messages exchanged between two participants should remain confidential in general. More strongly, in particular, should an adversary ever learn some session secrets, allowing them to decrypt some messages, for example, here the bottom 3 messages, then iMessage still aims to provide forward secrecy, meaning that messages exchanged previous to that compromise should remain confidential, and post-compromise security, meaning that participants should be able to recover secrecy after such a compromise and communicate securely in the future again. iMessage also aims to provide agreement and replay protection, and I guess replay protection is obvious what that property is. Agreement means that participants should have a shared view of their conversations with each other. So if I believe I'm talking to Kim, for example, I should actually be talking to Kim. iMessage intends to establish these security guarantees against a very strong adversary. So in general, we consider an active network adversary. That is an adversary who can intercept all messages that are sent on the wire, so there's no kind of transport security. They can reorder messages, they can drop them, they can send their own messages, provided they know all the contents they want to send, etc. Then now comes the PQ3 part. iMessage considers an adversary with particular quantum computing capabilities. It's a harvest now, decrypt later adversary. Such an adversary anticipates future developments in quantum computing and records all messages exchanged on the wire, which they see because they're an active network adversary. And in the future, should a quantum computer become available, they will try to do some offline attacks on these messages using quantum computing. We consider the harvest now, decrypt later adversary thus effectively as a passive quantum adversary. So as soon as they process a quantum computer, they cannot send their own messages anymore because the protocol will have already stopped running. And in general, we allow the adversary to compromise any key. And now you might wonder, well, if you compromise any key, is there any security? No, but in our security lemmas and properties, we will account for all these cases and say which security guarantee holds under which key compromise scenarios. So how does iMessage provide these security guarantees? iMessage follows a hybrid approach, and it combines classically secure elliptic curve Diffie-Hellman cryptography, which is well understood and has been used for, I presume, decades, with newer cryptography, which are post-quantum secure key encapsulation mechanisms, or KEMS for short. These provide the quantum security, but they come with a higher bandwidth cost, so iMessage has to use them sparingly. Both these primitives are used to derive shared secrets, Diffie-Hellman shared secrets and KEM shared secrets, and they are combined in a key derivation function together with what are called root keys that maintain cryptographic entropy from previous runs of the protocol into a new root key and what is called a chain key that you see on the left here. And this chain key is then used to derive a message encryption key, MK, and another chain key from which you can derive further message and chain keys. The upper part of this key derivation schedule is also called the public key ratchet because you use public key cryptography to derive shared secrets, which you use to establish other shared secrets. The lower part, marked in green here, is called the symmetric ratchet because you use the shared secrets established in the public key ratchet to derive symmetric encryption keys for the actual message encryption. Together, these two loops these two loops give you a nested loop, so the symmetric ratchet happens within the public key ratchet, and they closely resemble Signal's double ratchet construction that Signal invented a bunch of years ago. The novelty of iMessage is that it was the first protocol to introduce the chem in the double ratchet. Signal by now has presented their own proposal for making the Signal protocol itself quantum secure, but I'll ignore that today. And thus, iMessage can provide post-quantum, post-compromise security guarantees, as you will see later. Let's look at a concrete example. So imagine we have two participants exchanging 6 messages. In iMessage, each of these messages will be encrypted with a unique message encryption key here called MK, which is indexed here by message. In the beginning, the two participants will establish 2 shared secrets, a chem shared secret and a Diffie-Hellman shared secret. They combine that to derive a root key and the first chain key, and then a message encryption key to encrypt the first message. Then from that chain key, the same participant derives a new chain and message key to encrypt the second message. Whenever the conversation changes direction, participants will perform a step in the public key ratchet, and to save bandwidth, the chem shared secret will not be always updated, will be updated sometimes. This is based on a heuristic, so for all intents and purposes you can think about it. It's being updated non-deterministically. So for the sake of the example, in the first public key ratchet step here, only the Diffie-Hellman shared secret is updated, but not the chem shared secret. And from that again, we derive the next message encryption key. The conversation does not change direction, so we use the chain key to derive the next message encryption key, etc. Yeah, again, the upper part here is the public key ratchet, the lower is the symmetric ratchet. So far my introduction for the iMessage protocol. Our goals in our research were to understand iMessage's security goals thoroughly. They are well-established security goals, but for example, how you relate them precisely to the key material and compromise scenarios that we wanted to make precise. And then verify that that iMessage meets its security goals. And for that, we wanted to use the Tamarin prover. That is a tool that got developed in the information security group over 10 years ago now. You may have heard of it. I don't know. It doesn't really matter, but it's a bit older by now. The Tamarin prover Tamarin is also a monkey. This is our logo. It's the pixelated version of that monkey, and I need to tell you that it's a monkey. So A, you understand the logo, and B, I can make a small pun later. Tamarin is a protocol verifier, and it uses constraint solving, and it operates in the symbolic model. So the symbolic model is an abstraction of cryptography, as you'll see soon. We do not capture all details that cryptographers typically capture, but that allows us to consider typically larger systems. Tamarin has been used, for example, to verify and find attacks on protocols such as TLS 1.3, the 5G authenticated key agreement protocol, and the EMV protocol, which is the contactless, not just contactless, the protocol that credit cards, for example, run with payment terminals. But I have bad news for you. If you're to believe related work, then you'll find sentences like this, namely that unbounded looping protocols like Signal are unfortunately out of scope for symbolic provers without introducing artificial restrictions. And initially we thought that too when we started collaborating with Apple to analyze the protocol, but by me standing here, you probably already know the conclusion. So luckily we found that this is not the case. We were able to prove iMessage secure without any abstractions. I put a footnote there, yeah. And moreover, we provide a general proof methodology to do so. So what's the footnote with no abstractions? I just told you that, for example, we prove it secure in the symbolic model, which is itself an abstraction, but we do not introduce, let me call them non-standard abstractions beyond the abstractions that our tool already has by being the tool that it is. So let me give you an intuition for how the Tamarin prover works. When you model in a protocol in Tamarin, you model 2 things. You start typically by modeling the protocol using multi-set rewriting rules. These multi-set rewriting rules define a labeled state transition system. And the state transitions in that system typically model participant steps, so me, for example, sending a message, or they model the environment, for example, a non-deterministic assignment of keys to participants. With that, there is an equational theory, and that defines the cryptographic operations and how they work. And in particular, they are used to define the adversary capabilities. So for example, they will allow the adversary to decrypt messages when under certain conditions. At the bottom right here, you see two examples of equations, and these are the complete models of how signature verification and symmetric encryption work by default. And now you may see why we abstract cryptography to some extent. So the first equation states how signature verification works. It says that whenever you apply the verify function to correctly generated signature for some message under some secret key, and into that verify function you also pass the same message and the corresponding public key, that gives you true. So the signature verification passes. And for symmetric encryption or decryption respectively, whenever you symmetrically decrypt a symmetric encryption of some message under some key k, and you decrypt it with the same key k, then this gives you the message. In Tamarin, you can model, or you must model security properties as trace properties, where you refer to the labels of the transition system that you encoded in the multiset rewriting rules. These security properties are also called lemmas. And here you see a small example. This is an example formalization of message secrecy. It formalizes that for all participants P and messages M and time points X, whenever participant P sent message M at time point X, so yeah, this hash X is some time point, then we want that there does not exist another time point Y where the adversary knows that message. And this K stands for knowing. It's just the built-in formalization of Tamarin. So this message sent event, for example, that would be given by the modeler. The modeler would encode a multiset rewriting rule, say this is supposed to model that a participant sends some message, and we want that the adversary does not know that message. Yeah?
Is this some kind of temporal logic? Since you mentioned different
no, I mean, I think technically it's a fragment of first order logic.
Okay.
But we have these special time points, yeah? You can make you can do time point comparisons. So you can say, for example, time point X is smaller than Y, and then you have some order. So you can encode many temporal logic relations. Yeah, but I think technically it's a fragment of predicate logic, first order predicate logic.
First order. Okay.
Yeah, I think so. Yeah. So, what does Tamarin do with such properties? It uses constraint solving to prove them. How? It first starts by negating it. So what would this property be negated? It would be that there now exists a point in time where a message was sent and the adversary knows it. And then Tamarin will start a backward search to construct an attack trace for this property using all the rules it has available. Because Tamarin's constraint solving rules are sound and complete, a failure to construct an attack trace means that the original property is proven, and the success in constructing an attack trace means that there is an attack on the modeled protocol. Using these Tamarin features, let me provide you a rough overview of what our formal model all encodes. So our formal model has 3 phases. They are partially for just like illustration purposes. In the first phase, the setup phase, participants generate keys. They query each other's keys using an identity server, so modeling a key server, and they can start sessions. What we also do is, this will be important for the post-quantum phase, we memorize all key material that is non-post-quantum secure. We just put it on like a little transcript on the side. Then, in the protocol execution phase, we have 2 sets of rules. Sender-related rules that consume a session and update it by producing a new session and then additionally send some messages. And receiver-related rules that take some session and receive a message and then update their session correspondingly. Participants, by non-deterministic choice, can swap roles whenever they want. Again, we memorize ephemeral key material that is generated by participants during protocol execution on our little transcript on the side for the post-quantum secure phase. Let me just point out that this line here is just for illustration purposes. Yeah, so a participant that executed some receiver-related rules can still start new sessions. This is just to give you an illustration. So this barrier is permeable. However, the barrier to the post-quantum phase is non-permeable. So in our model, we allow, again, by non-deterministic choice, the adversary to transition into the post-quantum phase. And as soon as that happens, the adversary is allowed to access all classically secure secret key material that we put on the site to model the harvest now, decrypt later adversary. So our formal analysis of iMessage covers all 5 to 3, depending on how you look at it, security goals of iMessage. We prove secrecy, including forward secrecy and post-compromise security, agreement, so an authentication guarantee, and injective agreement, which formalizes replay protection. Now I would like to give you a small illustration of how our secrecy lemma works. So remember the key schedule that I showed you in the beginning, where we derive message encryption keys and root keys. What you see here is a small generalized version of that. Let's presume we're considering a message has been sent and encrypted under the message key MKK that is highlighted with the arrow here. So that means it was derived from some chain keys and some Chem shared sequence and Diffie-Hellman shared sequence, and there are also sessions in the past and in the future happening. Not sessions, sorry. There was key, like it's one session, but we are focusing on this point of the session. So in our secrecy lemma, we formalize that messages are secret unless at least one of the following types of compromise occur. Either the message encryption key got revealed to the adversary. Okay, I hope you're convinced that if they learn the exact message encryption key, the adversary is also able to learn the message. What could also happen is that the adversary learns one of the chain keys used to derive this message encryption key MK, or both the Chem shared secret and the Diffie-Hellman shared secret, which encodes the hybrid security guarantees that iMessage intends to provide. Let me highlight, but I think this is like you don't know enough about the protocol for you to understand this, but the adversary can effectively circumvent the requirement to learn the Chem shared secret by learning one of the previous root keys. That depends on the exact Chem key schedule and some protocol details. If you're curious about that, I encourage you to read the paper. But yeah, I wanted to include it for completeness. And then what can also happen is that signing keys by participant get compromised. So in iMessage, every participant signs their message, and if you learn these signing keys, you can impersonate a user straightforward. Let me highlight that we assume the adversary to know all other keys, or all keys in general, but all keys that are not highlighted in colors. And this gives us implicitly forward secrecy and post-compromise security guarantees in one security property. With respect to the message sent at the message encryption key MKK here, we provide forward secrecy to all the keys that will be revealed in the future to the adversary. The adversary knows all those keys, yet they cannot learn the message in question. And we have already recovered from the compromise of all the key material in the past. The adversary is also given that, yet learning this key material does not give them any advantage in learning the message key at the arrow. So now you may wonder, where's the quantum attacker now in this secrecy lemma? And the quantum attacker is in our actual formalization that we proved. It will become more apparent, but in this graph, it's hidden in how the adversary could learn key material. The post-quantum adversary will be trivially able to, for example, learn the Diffie-Hellman shared secret N at the top because they are quantum adversary, they can just like compute it, but they will not be able to learn the Chem shared secret because that uses post-quantum secure cryptography. That shows that the post-quantum attacker must repeatedly compromise all the established Chem shared secrets in order to learn all messages exchanged between two participants, giving us the exact post-compromise security guarantees we were looking for. Proving these properties was far from trivial. There was a reason that people thought it was not possible. So we proved 32 auxiliary lemmas to prove mainly secrecy. Proving agreement and replay protection was much easier because iMessage there relies on just the security of the signing keys. And checking, if you want to verify all the proofs on some computer, this will take you roughly 2 days of compute time. and 140 gigabytes of memory as maximum resident set size. We estimated, like I don't clock my hours, but we estimate that this was roughly 2.5 person months of work to get all the proofs and auxiliary lemmas right. But from this effort, we developed a general proof methodology, and I think we would be much quicker for other protocols now. And by anecdotal experience, I can confirm that. So I have had to prove protocols that follow a similar structure, and my own proof methodology helped me, luckily. As the results of our analysis, we find that iMessage PQ3 is secure in general. We did not find any attacks. But two positive outcomes of the analysis are that we now have formally specified security guarantees, including which keys may leak when. And during our collaboration with Apple, we refined the specification a bit. For example, we were required to add a small assumption to prove replay protection. That was not obvious to us in the beginning, but the assumption, was in hindsight, it was trivial. A second result of our proving is that we now are convinced that Tamarin can analyze protocols as complex as iMessage. And I hope you take away from this that although it took a considerable amount of time, you should and can use it. And if you're curious about the benefits that Tamarin can bring you in other use cases, please chat with me during the break. We have many stories on that. So in summary, in our paper, we proved 3 security guarantees: secrecy, including forward secrecy and post-compromise security, authentication and replay protection, using Tamarin, which fortunately worked better than anticipated. When we started collaborating with Apple, we told them, we'll do our best. Fortunately, the tool was up to the challenge. So Tamarin can analyze protocols as complex as iMessage. If you're curious about more details, I encourage you to read our paper. It's under the usenix.org link with this suffix, or just to ask me questions and chat with me during the breaks. Thank you for your time.
Good question. Given that you're using a composite, a classic, and post-quantum crypto, if I understood you, you modeled the scenario that the classic is broken because of cryptographically relevant quantum computer, right?
Yes.
Did you also try modeling the other side, that the classic crypto is not compromised, but the MLChem is compromised?
We did not explicitly model that, but since in our lemmas, or in our security properties, typically they are a big disjunction, yeah? So we say good things happen or one of these things goes wrong. And there is a branch that says you learned the the corresponding chem secret key, yeah? So now there are many scenarios why you learn it, right? Mm-hmm. Maybe the crypto is broken and you just learn it. Yep. Maybe you reveal it. So while we don't directly account for it, I would say revealing the key to the adversary has equivalent effect, right? Like whether you just reveal the key because you post it on Twitter or whether you reveal it because the crypto is broken.
Well, the reason I'm asking is that's assumption, right? But
yeah.
Given that you are using this tool to prove all of these, following your same logic, if there was an attack found, that means that there's an attack. Otherwise, it means that we have nothing to worry. That is what we are hoping,
yes.
or expecting. So I was just curious why you make that decision.
Well, you can also, let me maybe rephrase what I said before. In our security properties, we say to break the secrecy of this particular message, you need to know these keys, right? Okay. Our model, to some extent, abstracts from why you know them. If you know the key because your phone got compromised with malware and they extract it, or if the adversary compromises the post-quantum crypto because the post-quantum crypto is broken, right? The cause for the adversary knowing the respective secret key or being able to control that cryptographic primitive, that's not encoded, but we consider the case that they can break it.
Okay.
Yeah?
Jonathan?
Can I get a sense of the how much manual intervention you required for this proof? You said that you had to write lemmas. I'm also wondering about the inductive invariant because you stated that you did not analyze a bounded set
Yes,
of ratchets, right?
yes.
You said unbounded. So
Unbounded, yeah.
did you write the inductive invariant by
Yes.
hand? Okay. And
So I would.
how hard was it to come up with it?
How hard? On a scale from 1 to 10? So, no, to give you an idea, I would say the automation really only helped in getting the prover to terminate on a lot of cases. Yeah, I would say this was a manual proof, a computer-aided manual proof. The computer checked it, and sometimes, especially with the commutativity that you get from the Diffie-Hellman crypto, you get a lot of case splits, and then the computer helps you to check your proof methodology on all the case splits. But the proving itself, only at the, after, I would say the secrecy lemma itself, that's actually trivial to prove, but just because we have so many auxiliary lemmas. So it's just, it's basically just reasoning on the formula level.
I have more questions. Can I follow up? How different is this from signal? It seems like you were describing it's almost exactly signal. Are there any substantial differences?
Which signal now? The post-quantum secure one or the non?
I'm only familiar with the non. I'm not familiar with
I would say it's an extension of signal. There is a difference in that Apple uses signing keys, so they do not have deniability guarantees. And I think that helps with the analysis because with signal, I also proved signal for a different paper with some less key reveal possibilities, and there you need to make other inductive invariants because you more strongly rely on the secrecy of past sessions. Yeah, because in iMessage every message is signed, that gives you some stronger guarantees of the key material actually originating from an honest participant. But my gut feeling would be it's an extension of signal that has non-deniability. The public key, like all the key derivations, they are pretty much the same, I'd say. But footnote, I know iMessage much better now than signal. So yeah, maybe I also misremember how signal exactly works.
Thank you.
Yes, actually, I want to ask about some details on the signature. So the secrecy property that you presented depends on the secrecy of the signing key.
Yeah.
So it's a bit surprising. So it's just because you can impersonate a person and then get someone to reveal the previous message, or what is the freshness of that assumption?
You need this with the signing key. I can just start a new session with you. So.
Yeah, but you would not be able to decrypt legitimate message from other sessions. You just the message.
Yeah. In our lemma, we say the signing key must have been compromised before the message was sent. Yes.
Before the message was sent.
Yeah.
Okay.
In the question of like this one with the arrow,
Okay. And the signing is not post-quantum.
No, the signing is not post-quantum. Yeah.
So in fact, the post-quantum security kind of doesn't work against the quantum break of the signing algorithm.
That's why I said we harvest now, decrypt later adversary. We consider to be like a passive quantum adversary.
Okay.
Yeah, as soon as you our assumption was as soon as you enter the post-quantum phase, all honest participants stop the protocol.
Okay.
They
So
don't.
there's no more message after the.
Yeah.
Okay.
Yeah, I'm wondering, explicitly you model cryptographic agility, so do you consider security with multiple choice between multiple elliptic curve for the Diffie-Hellman part, or multiple key strengths for MLCAM?
No, we didn't. But also, I don't think you would gain much there in the symbolic model. There are better ways to model cryptographic primitives than we used. There's a line of work by Cas Kremers, and I've started following his approach with newer analysis, and I think it's better, and there's a lot of value in that. So maybe there you could get... So with a student, I looked at, for example, whether the security analysis changes if you consider different binding properties of the chem, but we found out no, it doesn't, because every message is signed. So you get the very strong binding from the message signatures being used already, and how strong the chem is now binding is of secondary concern. This is something you could analyze, but yeah, I would say precise difference between the cryptographic primitives are hard to capture in the symbolic model anyways. But it would depend, like I'm not familiar with all these details, so maybe I'm too pessimistic, you know. Yeah.
Maybe you can discuss that a lot.
Yeah. Yeah.
Well, let's. More questions?
Yeah, so it's very impressive that you work with Apple engineers on this. I guess in the beginning, they knew more about the protocol than you, and you knew more about the formal method than them.
Mm-hmm.
Then, in the end, do you think that they understand what you have done, or you just convey the final conclusion to them?
I mean, it's hard to speculate about other people's state of mind. I mean, the mere fact that I hope that after 5 years of doing a PhD, I understand more about Tamarin than the people at Apple. So to some extent, that is to be expected. But I mean, they approached us because they wanted this to happen. So I think they had a pretty good understanding of what the tool in general is capable of giving you. Yeah, and I don't think their understanding radically changed through our approach. Yeah. So, yeah.
Thank you. Well, let's thank Felix again.